So I was thinking about doing sorting today, but I'm willing to do something else if we need to. Yeah, so we did this and sorting here. We talked about vectors, right? We did that. Yeah. So any questions about the assignments or anything like that?
I just have a question on number 9. I'm not really too sure how to think about a question.
The assignments, a question about what?
The vectors, number 9.
Which one?
It's the one that's talking about the vector flattening.
Yeah.
I'm just a little confused on how to really
The flatten.
Yeah.
So there's a assignment on I think it's the last problem, flatten here. Let's take a look at that. We just let's see that. So in this problem, we need to implement this function called flatten. And flatten flatten takes an array that's 100 by 200, and it produces a vector of int. So you can sort of look at a smaller example to get a better understanding. So if you have an array, say 2 rows by 3 columns, there's an array that's 2 rows by 3 columns. It's like an array of 100 rows by 200 columns. It's just a smaller example. And so this would be A. And then the resulting vector would just be this thing flattened out. So it would look like this. That's it. Just take, put the first row on V, then put the second row on V, put the third row on V. That's it. So you use the operation. You're going to need pushback on that operation. Put in some value here, right? From a value from A. Start with then at the end of the function you return B. You'll need some loops in there, more than one, because you have rows and columns to go through. So for each row, you want to run through all the columns in that row. So for this row, you start with column 0, and then you push that in there. Then you go to column 1 and push that onto V, and then column 2, the third column, push that onto V, and then when you finish pushing all the values from this first row, you go to the next row, and then you do the same thing. Keep pushing the values one after another as you increment the column index. Make that a little smaller. Is that okay? Yeah. Let's look at sorting. In fact, we got a nice example right here. Let's sort this. So we start with this, sorting means putting things in order. Now 2 is already in the right place. Oh, no, it's not. -7 is less than 2. So what we want to do is go through some algorithm, some process, rearrange these values, and put them into sorted order. And that's what I'm doing right here. See that? But how did I just do that? I mean, in my mind. I used an algorithm in my head. And, I mean, it's simple to do, right? It's trivial to do. But then how to code it up, that's all of a sudden it becomes a hard problem. But if you just do it without thinking, it's trivial. So I'll tell you what I think I did. I looked there, I said, all right, well, what's the lowest value? I have to scan across, I got some I here, like an index, and I'm scanning across the list, and I say, okay, 2 is small, and 4 is bigger, so I can ignore that. -7, oh, that's smaller than what I got 2, so, -7 is the smallest so far. 4, no, it's not smaller than -7. 9, no, that's not smaller than -7. 10, no, that's not smaller than -7. So -7 must be the smallest number. That's going to start the list. I did that in my head, but in a fraction of a second, right? You could just. I even made the decision on the algorithm to use. I mean, I'm just assuming that everybody does a similar thing. You might have a different algorithm, but there's you solve this problem. Now, after the -7 is there, it's like, okay, what's the next smallest? Well, the next smallest. Well, I'm going to start the whole process again, right? The next smallest is 2. Okay. 4, -7, 4, 9, 10. Well, the -7 we already got, so I made a note. Can't be that. We've already got that. So it must be this. Must be the 2. So I'll put the 2 on there. All right. What's the next smallest? Now we got this 2 on there. So maybe 4 is the next smallest. Well, it's not -7. We already got that one. Well, there's another 4. Did I get that right? I thought there was two. There's two. I thought there were 2 2s. Did I do that wrong? No, that's right. Okay. Oh, so it's a second 4, and so it must be 4. 4 is next. You see this index? I'm running this along here. We got that one. We got that one. But this one, that's the second 4. We need to get that on there. And I didn't do it, but my eye ran across just to check to see if I had something less than 4 over there. So I'm using this I because we're going to have a loop that controls this, right? We're going to keep running through the list. In fact, I'm going to use J here. I'll show you that in a minute. So we got these. Then our 9 is a possibility. Well, 9 is less than 10, so it's got to be a 9. And then the last one, to put that on there. So let's refine that a bit. Let's do that again. Oops. What was it? It was 2, 4, -7, 4. I'm going to shuffle things around a bit. 10, 9, and 4. We're doing what's called an in-place sort. So we don't want to copy the vector. We want to do everything in place here. So we're going to start with I here. And where I is in the position 0. We want to get the smallest value in this position that I points to. So we're going to use a J here. I'll do it on the top. We're going to run across the array looking for a value that's less than the one that's in I, at position I. So we start here at 4 at the second slot. 4 is not less than I. Then we advance J, minus 7. Oh, minus 7 is less than the value at I. So I'm going to swap those two. So now minus 7 goes into the first position. And 2 takes the place where minus 7 was. So I swap them. Now we're going to keep running down the list with J, looking for a value that's smaller than the one at I. I don't see anything smaller than minus 7. So now we finished that outer loop. So we advance. That means what we have is we've got the right number in the first slot. Now we're going to check the second slot. So we advance I to the second slot, or slot 1, position 1. And then J is reset to the third position. There's no reason to look at the second position. We just bring it back to the third position. And now we start the process again. Is the value at J less than the value at I? It is. All right, let's swap. 4 and 2. Advance J. Is the value at J less than the value at I? No. Advance J. Is the value at J less than the value at I? No. Is the value at J less than the value of I? No. So that means the first two positions are taken care of. So it's like this I is cleaning things up. Everything to the left of I is done. Everything to the left of I is where it's going to be at the end of the process. Everything from I to the right is yet to be determined. So you see we're making the range of concern is getting smaller and smaller. We're leaving behind us a trail of sorted values. Now we need to reset J. And we reset J to one position past I. Is the value at J less than the value at I? No. Is the value at J less than the value at I? No. Is the value at J less than the value of I? No. Oh, J is not valid anymore. We're done. Third position is taken care of. Advance I. Set J to 1 past I. Start the process again. Is the value at J less than the value at I? Yes. Okay, let's swap. So we swapped. Let's advance J. Is the value at J less than the value at I? It is, yes. And we're going to swap this one. We had to do 2 swaps to get this one into this position that we want. And then J goes past the end, so we're done. All right, everything from I to the left of it is finished. So we have to keep squeezing, smaller and smaller range here. And then we set J to 1 past I. Is the value at J less than the value at I? Yes. Let's swap. Advance J. Oh, J is past the end. So then we advance I. I is at the end. There's no values to potentially swap with, so we just terminate here. So there it is. If you can see the list there, minus 7, 2, 4, 4, 9, and 10, we just applied that algorithm and we sorted the values. And now the problem is to code it up. So let's call it, I think I called it, what, my sort? Did we do vectors? We did vectors, right? Okay. Should we do this with vectors or arrays? What would you like to see? Vectors. Okay. So it's a vector of int v. We're going to make it a reference, okay? We don't want a copy of v. We're not going to sort a copy of v. We want to sort the v itself, okay? So we've got to make it a reference, otherwise we won't, we're just going to sort a copy. And also we don't want to declare it const because we need to modify v. It's not const. Those are the two decisions you make when you declare a parameter. So you've got, remember this I is in the outer slower loop and j is in the faster inner loop. This is like the minute hand on a clock and this is like the hour hand. And let's remember, what did we do? We started I at position 0, right? We started I way over here. And we continued with I until I hit, this is size -1, right? This position, which is past the end, that's the position equal to size of v. This is the last position because we start counting at 0. The last position is position size -1. When we hit position size -1, we were done. So we don't need to execute the loop logic when we hit size -1. That means we can stop at size -2. We stop when wait a minute. So this is size -1. I'm going to get confused now. This is size. This is size -1. When we hit size -1, we're done. So when I is size -1, this is false. So we're finished the loop. So I think I'm okay with that. It's a one-off problem. Made me nervous. All right. So there I is ranging, the slow moving index I is ranging across those indices. So now what about the faster moving index j? Remember j, the way we always did j was, when we did this, we set j to 1 past the position of I. So if I were in this position, position 2, then we would set j to position 3. So j is 1 past I. So we initialize j to I plus 1. And then we run j until it goes past the end of the array. So it's v dot size. When j hits v dot size, it's past the end of the array. This loop condition becomes false, because that's what we want. And then we're incrementing j. And then, so we've got I and j running just the way we want. Now what we need to do is compare the value at I with the value at j. If the value at I is less than the value at j, then we're going to swap those two values. And that's it. That's all we do. Now I used a different sort of method of development here. We didn't develop the test cases yet. So we didn't do that. Let's go ahead and do the test cases now. So we have a vector v, a vector of int. And we're going to call pushback on v many times. Sorry about that. Push back several times. Those are the numbers I want to use. There's 6 of them. And let's put a 2 on there first. That's how we did it, I think. It was 2 and then 4. Actually, I don't remember. -7, 10, 9, 4. I think that's how we did it. And then after we push those values on there, let's call my sort. I call it my sort because there's a function called sort that's in the standard library, so I didn't want a name conflict there. Just want to sort V. And now we'll use the assertions. So V of 0 needs to be -7. And let's do the others. We've got V of 1, V of 2, V of 3, 4, and 5. And the next position is 2, and then is 4. And 4 again, 9, and 10. That's the sorted. So there's our test code. Got something wrong. Anybody see the problem? Here it is. Error. Variable or field my sort declared void. Variable or field my sort declared void. I don't see the problem. Oh.
If it's void, I thought voids don't have return types. Or don't return anything.
Yeah, so I don't return anything here. Maybe I need to use the, you know what it is? It's the using namespace standard, believe it or not. That's what I think it is.
You have it right there too again, after the void.
Oh, I had it down here. That means, see, let me show you here. See, it's seen this vector. It doesn't know what vector is. I have to tell it it's in the standard namespace. I can prefix it. Now, I don't need this. This declaration came after I used the name vector. So if I use this, but also swap is also in the standard namespace. So, oops, not in BI. Let's see if that fixes it. It does. But that's, yeah, it's inconvenient, right? So let's put this up here. This just simplifies the code a bit. Some programmers will never do this because we're importing every name from the standard namespace. If we wanted to be restrictive, I think we can do this. I think we can do that. Is that syntax good? I've never done this before. That doesn't work. Oh, endl and cout. I got to use those too. So if you want to be a purist and not import all the names from std because there's a lot of them, then you could use this process here. There it is. That works. Assertion failed. Look at that. We got a bug. Oh, that's exciting, huh? All right. So that's another way to do that. I'll just clean that up to make it, it's such a small program this doesn't hurt. So we have an assertion failure. V of 7 is not minus 7. Sorry, V of 0 is not minus 7. This assertion failed right there. That means we got this wrong. What could it be? The if statement? I got it backwards, right? That's right. Good. Now it's getting toward the end of the quarter, you're getting faster than me now, right? That's the way it's supposed to be, right? Exactly. All tests passed. We got it. All right. Okay. There's other ways to do sorting. This is just one way. Oh, and by the way, this is an inefficient way to sort. I'm going to demonstrate that to you. I'm going to include C standard live. I'm going to use a random number generator. I'm going to seed the random number generator first. There's our sort routine right there. And then for integer I equals 0, I less than 200,000. Let's create a vector with 200,000 random integers in it. There's a vector with 200,000 random integers. And then we're going to sort that. We've determined from our test code, although the test code is not too extensive, that our sort program is working. Seed the random number generator, create an empty vector, push back 200,000 random numbers, call my sort, and then print done. Because we don't want to say tests, right? Because we're not doing a test. Now that's a lot of numbers to sort. So the question is, how long is it going to take to finish? I just started it, okay? So it'll take a while. And so this is running pretty slow. I'm going to rename this to slow. It's still running, isn't it? We're not running the source code. I just changed the name of the source code. We're running the executable a.out. And let's go ahead and, while we're waiting for that to run, let's copy that file and paste in the copy. And I'm going to show you a fast version of this code. Still running down there, isn't it? Instead of calling sort, I'm going to call sort that's part of the standard library. It's in a header called algorithm or algorithms. I can't remember. I think it's algorithm. And sort, it's a little cryptic, but sort is going to start, it takes two arguments, V0 And I can't remember now. It takes a reference, right? So this is v dot begin and v dot end. So you want to sort from the beginning of v to the end of v. It's still running down here. Maybe the numbers are too many. It is still running. Can you believe it? Let's open up another terminal window. And I'm going to compile fast. But I want the output to be, we're going to call it, we're going to call it executable fast. Did this finish yet? No. That's still running. That's a dot out. So I didn't want to clobber a dot out that's running now, so I generated the executable. I named the executable fast. Use that -O for output. Output is named fast. So we're still sorting 200,000 random integers there using the sort routine we figured out. Let's go ahead and let's run the sort routine that uses the sort routine that's built into the standard library. All right, you ready? I want you to count the seconds, okay? That's less than a second. Is that amazing? Is that amazing? It sorted 200,000 random numbers in less than a second, and our routine is still running. Is that amazing? So there's a big difference, and this is an area that we want to talk about a little bit here, but without getting it into details. Algorithm design or algorithm analysis. The algorithm that we came up with is inefficient. It's not as efficient as it could be. There's a more efficient algorithm. It's an algorithm that can run faster. In fact, this algorithm that we came up with, the number of times, the problem is in here, this comparison right here, the number of times that comparison runs is proportional to the size of the vector squared. So the time to complete this thing, the time to run, the running time, call it running time. The running time is some constant, some proportion, times the number of values in V squared. So as the size of V gets large, the time just blows up. Now over here, in fast, the running time is not C times n squared, it's C times n times the log of n. Now the log of n grows very slowly. When n is, 1024, let's suppose that n is 1024. That's a kilobyte, right? So that's 2 to the 10. When n is 1024, the time is some constant times 1024 times 10. Did you just see that? It just finished. Did you see that? That just finished. Just to show you the difference, I'm going to run fast one more time. Look at that. I didn't even lift my finger up off the key before print done. That is amazing. The difference is phenomenal. So here, for 1024, in the fast algorithm, we're getting this. The time is going to be, some constant times 1024 times 10. So like 10,000. But if the running time is if we use n squared, and n is 1024, and the time is going to be, c times 1024 times 1024, and that's a million. Yeah, approximately a million. So you see, and our n went to 200,000. So 200,000 squared is just blowing up. But when you take the logarithm of 200,000, you get a small number. So that means when you multiply by n, by a small number, it doesn't get too bad. It doesn't blow up as fast. It still goes to infinity, but it doesn't get there that fast. So this is the study of algorithms, and it's a major area in computer science. So we have a course here called Algorithm Analysis, and it's one of the major areas in computer science. All the theory of computer science is based mostly on, not mostly, but a lot of it on algorithms and their analysis. Oh, here's the sorting lab here. So you implement my sort, and then the slow and the fast, I kind of showed you how to do it already. And that's it. That's this assignment. So it's going to be kind of easy on you there. It's not a lot to do. I used 100,000 here, but every year I have to increase the number a little bit because it's the machines go faster all the time. So maybe 100,000 runs too fast. Let's try that. Let me try that 100,000 here. So if we used 100,000. So that took several minutes, right, to run. How long, if I cut it in half, how fast, oh, and it's slow. How much faster do you think it's going to run if I cut it in half like that? How many seconds do you think it'll take? Or minutes? But the last one took, what, 20 minutes? 15 minutes? And we just cut it from 200,000 to 100,000. I'm going to take a guess, okay? I'm going to guess it'll complete in 4 seconds. 1 1,000, 2 1,000, 3 1,000, 4 1,000. I'm wrong. It'd still take a long time. It's still big. It is big. I don't want to give up on it. It's got to do it. No, that's too much. How about if we cut that in half? We go down to 50,000. Yeah, maybe it's that slow virtual machine. That's what it is. If I had this on my local system, let's see. I'm going to play around a little bit. How about if we put it on the local system here? Oh, that finished. Did you see it? Done. Not too bad. All right, here it is on my Macintosh. Oh, that's still pretty slow too. 50,000. Yep, that's slow. That is slow. So maybe 100,000 is okay. Eric finished. What time is it? All right. So that is sorting. There's a lot more to talk about there. I'm not getting into the math more than that. And there's other sorting procedures that you can use. There's this thing called bubble sort and other stuff. But I'm just leave it at that to keep it simple. And we have exam 2 coming up. Today's May 11. I need to make that exam actually. So this exam 2 will cover up to and including vectors. Is that what I said here? Yeah, so I've got vectors in here. And search. I think I should put sorting in there as well. Exam 1 and exam 2. Oh yeah, including sorting. Okay, so this is the last topic for the second exam. And exam 2 looks like this. Just implement this function. You know, is A and B, are A and B identical? Return the smallest value in V. Min value. Count negatives. Is a two-dimensional array. How many negative numbers are stored in that array? These are exam problems, okay? Search, linear search. The numbers are not in order, so cannot use binary search. Linear search. And how about this one? Binary search. Implement binary search with vectors. Find the position of K and V. That's an int. I could have returned a bool. Tell me if K is in V or not. In V or not. True or false. So you just need to practice these. These problems you have to practice, but all of the other problems from the vector assignment. All of these appeared on one of my exams in the past. Every one of these was on an exam in the past. So you're just going to get skillful in working with vectors and arrays and binary search and sorting. That's the main focus. Anything you want to talk about? Nope. Okay, that's it then. Finished today.
I had a question.
Ah, all right.
So I was kind of Googling to see how long, like if there was an algorithm that would show you how long your program takes to run.
Yeah.
And I kind of found one that uses the time function.
Yeah.
And then it returns how many milliseconds.
Yeah, that's good.
I was wondering if you could like explain it, how it works.
Well, you got to take like here, you're going to print the time, whatever it is. I don't know if that'll print the time. And then here you print the time again, and you just calculate the difference. Or you could do, it's not an int, it's something, a long int maybe. I think it's a long int. Some time function you call. And then, so this would be the start time. And then you want the end time. So you call the start, you record the start time. Oh, sorry, this is not right. Start time equals, and I don't know if this is the right expression. Okay, we can look at that. And then we record the end time. And then we just calculate the difference. It's the end time minus the start time. I'm going to print that out. But I don't know what that produces. clock. So, you know, they show it to you right here. We just take that. So we call this function clock, and it returns a value of type clock t. And then the elapsed time is a value of type clock t. So, you know, we have start. So we call clock again. We subtract the start time, which we saved here. And then we divide by clocks per second. So it's clock ticks per second. So that gives us a value in seconds. Oops, not in VI. So let's go to 10,000 here. Let's see, it probably won't compile because, oh, it does compile. 0 seconds, 20,000. 3 seconds, 25,000. 5 seconds, you know, that's how you do it. Well, it's one way to do it. So this is a nice site. This is the links that I give you for reading or go into this site actually. It's one of the tutorials here. It was the, wasn't that one, this one. I think this is, I looked around before the class started, I looked around to find the best sort of online presentation of the language, and this is what I thought was the best. It covers a lot of topics here, and it doesn't cover everything, but it's a pretty complete overview. And so we've looked at a subset of these topics. All right, anything else? That's it. Okay, that's